Welcome to Hot Chips 33. Session 5. ML Inference for the Cloud.
We have a great set of talks lined up. We will start with Esperanto's AI Accelerator, which packs more than 1,000 RISC-V cores on a single chip, and then uses a variety of techniques in order to achieve near-optimal energy efficiency. From there, we will move to Enflame's AI Accelerator named the DTU1, with its scalable VLIW architecture for accelerating both inference and training workloads. And finally, we'll conclude with Qualcomm's Cloud AI 100, which targets both edge and data center inference workload with a single device. So very exciting. Let's get started. First up is Dave Ditzel. Dave is the founder and executive chairman of Esperanto Technologies. Prior to Esperanto, he spent 6 years at Intel as the VP of hybrid computing, and prior to that, he was the founder and CEO of Transmeta. And a fun fact, Dave was also the co-chairman of Hot Chips 1 back in 1989. Today, Dave will talk about Esperanto's first product and describe how they achieve near-optimal energy efficiency for machine learning recommender models. So Dave, the floor is yours.
Good morning, and welcome again to Hot Chips 33. I'm Dave Ditzel, founder and executive chairman of Esperanto Technologies. Today, I'm going to talk about how Esperanto accelerates machine learning recommendation workloads using over 1,000 RISC-V processors on a chip. The Esperanto supercomputer on a chip, version 1, is the world's highest performance commercial RISC-V chip. On one 7-nanometer chip, we put 1,088 energy-efficient ET minion RISC-V processors, each with its own vector tensor unit, 4 high-performance ET Maxion RISC-V processors, over 160 million bytes of on-chip SRAM, and interfaces for external DRAM and flash memory. The chip can be operated as a standalone processor or as an accelerator connected over a PCIe bus interface. The chip can compute at peak rates between 100 and 200 teraops, depending on the operating frequencies, and it's able to operate using less than 20 watts of power. Over 1,000 general-purpose RISC-V processors can be put to work on many parallelizable workloads. But today, we're going to focus on compelling performance per watt that this chip can provide for machine learning recommendation models, as recommendation is one of the most important problems for many hyperscale data centers. Now, machine learning recommendation workloads in hyperscale data centers have some of the most demanding performance and memory requirements, and have been largely run on x86 servers. Demand for additional performance is growing rapidly, and rather than simply building more data centers and buying more servers, customers would like a way to increase the performance for inference on servers they already have installed. Often these servers have an available slot for a PCIe accelerator card, but it needs to meet some key requirements. First, the performance of the accelerator card needs to be substantially higher than the performance of the x86 toast CPU, which means the card needs to reach computation rates of 100 to 1,000 teraops. Second, the accelerator card has to fit into existing infrastructure, where there may only be one PCIe slot available per server, and that slot will have a limited power budget, typically 75 to 120 watts. Google just published a paper on 10 key lessons from their TPU design experience. And one of those lessons is that for inference deployment at global scale, solutions must be air-cooled. So low power was very important. While a lot of inference can be done with 8-bit integer data, customers were also telling us that any solution needs to include support for both 16-bit and 32-bit floating point. An accelerator card should also have at least 100 gigabytes of storage in order to avoid excessive movement of data from the host. Having around 100 megabytes of on-die memory can significantly improve performance and substantially reduce many off-die memory references, which in turn can increase performance and reduce power. Recommendation problems have both dense compute and very large sparse memory accesses. In this way, they're quite different from the purely dense compute CNN operations one might see in the ResNet 50 benchmark. Computation mixed with very large, sparsely accessed data is challenging because the latencies to off-chip memory are very large, which may cause processing to stall. Finally, because machine learning workloads are evolving rapidly, fixed function hardware can quickly become obsolete. So the use of more general purpose programmable solutions is highly recommended. Esperanto picked the RISC-V instruction set as the foundation for our general purpose programmable solution. Now, let me explain how Esperanto's approach is different from some other inference accelerators and why we think Esperanto has a better approach, particularly for recommendation. Some of the other solutions use one giant hot chip that uses up the entire power budget of the accelerator card. Esperanto's approach is to use multiple low power chips that still fit within the power budget. There are a limited number of pins that one can practically put on a single chip package. So one chip solutions cannot go wide to get memory bandwidth and often end up with expensive memory solutions such as HBM DRAM. Esperanto's approach distributes the processing and I/O across multiple chips. As more chips are added, performance increases, memory capacity increases, memory bandwidth increases, and low power and low cost DRAM solutions become a practical solution. Use of systolic array multipliers is common in other AI chips, and this does work well for dense computations like CNNs and can generate great ResNet 50 scores. But depending on overly optimized hardware often comes with a lack of flexibility, and often these solutions don't perform nearly as well when there are sparse memory accesses to off-chip memory. Esperanto avoids this over-specialization by using thousands of RISC-V cores as the basis for computation. RISC-V provides a general-purpose instruction set, and we've added a number of vector and tensor instructions to further speed up the number of arithmetic operations per clock. This results in a far more flexible, programmable solution than many other accelerators. And for sparse accesses to large memory, the Esperanto solution provides thousands of threads to help deal with long memory latencies. On a chip with only a handful of CPU cores, anytime the problem does not map exactly onto the specialized accelerator, the amount of parallelism is limited by the small number of cores. In the Esperanto solution, the full parallelism of thousands of cores is always available to speed up execution. Single chip solutions often push for the highest operating frequencies, but this comes with very high power and is not very energy efficient. Esperanto realized that transistors, particularly 7-nanometer FinFETs, are much more energy efficient when operated at low voltages. Low voltage operation also significantly reduces operating power. To take advantage of this low voltage energy efficiency required substantial innovations to both circuits and modifications of the RISC-V core itself. Esperanto's challenge was how to put the highest recommendation performance onto a single PCIe-based accelerator card using no more than 6 of our chips and no more than 120 watts. Well, we could fit 6 chips on a 120-watt card if each chip took less than 20 watts. For simplicity of this example, we assume we could use 10 of those 20 watts for the 1,000 RISC-V cores, meaning that each core could only use about 10 milliwatts. Power is simply CV squared F plus leakage. And to see how big an improvement we are proposing versus a conventional server chip, let's imagine these basic parameters for some hypothetical x86 CPU core. If this imaginary core took 165 watts for 24 cores, that would imply that each core would take about 7 watts. We can also guess that at 0.85 volts, it could reach a frequency of 3 gigahertz. And assuming 30% leakage, that means it would have a dynamic switching capacitance of 2.2 nanofarads. Now, in order for our ET minion core to operate using only 10 milliwatts of power, we'd have to get the overall power down by a factor of 700, which was quite a challenge. It was fairly easy to reduce operating frequency down by 3x to 1 gigahertz. That's just turning down the clock. We could also reduce the operating voltage by at least a factor of 2. And since power is related to voltage squared, that would save another factor of 4x. But to operate robustly at low voltages is hard. We had to make a number of circuit and architecture changes. Operating at gigahertz levels at low voltages required designing with a very small number of gates per pipeline stage. Fab-supplied DES-NRAM cells also do not work at these low voltages. So Esperanto had to make both circuit and architecture changes for level 1 caches and register files. Even with these changes, there was still a gap of over 50x. And the only way to make up this difference is to reduce the dynamic switching capacitance. Dynamic switching capacitance is the capacitance from each transistor and wire and how frequently those switch. And to reduce those, you must have a very simple architecture with very few logic gates. This is where RISC-V was a great solution for a base instruction set, as it can be implemented with the fewest logic gates of any commercially viable instruction set. We also had to design our vector tensor unit very carefully as well. Now, let me show you an experiment we did that demonstrates the value of low voltage operation in achieving the best recommendation performance for our 120-watt card using a maximum of 6 chips. Here's a graph of the energy efficiency of 1,000 ET minion cores running our internal recommendation benchmark at different operating voltages. In this experiment, we modeled the cores as being resynthesized for each particular voltage point. As a core optimized for high voltage and high frequency will have more capacitance from bigger buffers to overcome wire delay than a core optimized for lower operating voltages. And for simplicity of this example, let's just assume that the only power we have to worry about is the Esperanto chip. Now, a common approach would be to try and run at the highest voltage to get the highest frequency. But if we did this, just one of our chips might use 275 watts, way over the 120-watt limit. So this does not work. Reducing the operating voltage to 0.75 volts, the nominal voltage in 7 nanometer, would result in 164-watt chip, still way too high. Just to get under 120 watts of power on a single chip, we'd have to reduce the operating voltage of the minions to about 0.67 volts. But then that one chip would use up the entire power budget. But if we operate at the best energy efficiency point, the entire chip would consume only 8.5 watts, and the 6 chips would fit in the 120-watt budget with room to spare. Now, with 6 chips, the performance would be 2.5 times better than the 118-watt single chip solution, and the energy efficiency 20 times better than trying to operate at the highest voltage. To maximize performance, though, we should use up the entire available power budget. And if we operate around 0.4 volts, one chip would take about 20 watts, meaning we could use 6 chips and still be within the 120-watt power budget. Esperanto's sweet spot for achieving best performance will be usually for operating our ET minions between 300 and 500 millivolts, that is nearest the best energy efficiency points. And by using the entire available power budget, we're 4 times better recommendation performance than a one-chip solution. Low voltage operation is a key differentiator for Esperanto's ET minion design. Now, let's see how the entire chip is put together, starting with the ET minion. The ET minion is our proprietary custom-built processor compatible with the 64-bit RISC-V integer instruction set. The RISC-V integer pipeline is shown in yellow in the roughly to scale block diagram at the right. Esperanto has its own tensor vector unit optimized for common machine learning data types. And you can see that the vector tensor unit takes far more area than the integer pipeline, supporting our premise that the area overhead for RISC-V is small. The core uses an in-order pipeline optimized to have very few gates per pipeline stage to improve megahertz when operated at low voltages. 2 hardware threads of execution are supported. To simplify physical design on the chip, the entire processor operates on a single low voltage power plane. The vector tensor unit is optimized for 8-bit integer, 16-bit floating point, and 32-bit floating point operations, which are the common ML data types used for inference. Integer operations were deemed the most important, and the core can operate on 512 bits per cycle, resulting in 128 8-bit operations per cycle, with the results accumulating to 32-bit integers. Floating point operations can be processed 256 bits wide per cycle, resulting in 16 32-bit single precision operations per cycle, or 32 16-bit half precision operations per cycle. As a large percentage of execution time is spent performing tensor operations, Esperanto added new tensor instructions, and these greatly improve execution efficiency. Tensor instructions can utilize the full vector width every cycle and run for up to 512 cycles, meaning that a single tensor instructions can compute up to 64,000 operations. Tensor instructions manage data movement as well as compute, and can utilize the data caches as a scratchpad for more efficient operation. This greatly reduces instruction fetch bandwidth requirements, which in turn reduces power consumption. During these long tensor instructions, the RISC-V integer pipeline is put to sleep, further making the overhead for providing RISC-V compatibility almost negligible. Physical design plays an important role, as you can only go a limited distance in a single clock cycle, and 7-nanometer wires are relatively slow. We found it convenient to group 8 minion cores together before wire length became a problem. These groups of 8 minion cores are called a neighborhood, and we were able to use their physical proximity to make several architectural improvements. We're able to save power and improve performance by allowing these neighborhood cores to closely cooperate. For example, 8 minion cores share a single large instruction cache. This was far more efficient than having each core have its own instruction cache with redundant copies of the same code. Another example, when one minion is doing a load from the second level cache, it's likely that the other 7 minions are going to be fetching the same data. Rather than doing 8 separate loads from the level 2 cache of the same data, we have a cooperative load feature that allows all 8 minions to receive the data using only one transfer from the L2 cache. These are just a few of the Esperanto innovations that allow highly parallel programs to compute more effectively than an array of standard processors. Now, 4 of these 8 core neighborhoods are put together along with 4 megabytes of memory to form a 32 core minion shire. Each bank can be partitioned by the software to be either an L2 private cache to that shire as scratchpad memory, or as L3 cache globally accessible across the entire chip via global shared address space. Dense memory cells are required for these 1 megabyte SRAM banks, and they have to be operated at nominal supply voltages. Shires are connected to each other via an on-chip mesh interconnect on each shire. And to save power, the mesh stop and its very wide interconnect is also operated on a low voltage domain. To enhance the performance of these cooperating parallel processes, Esperanto has also added several new synchronization primitives. Here's another picture of how the shires are connected with the on-chip mesh. Now we can see how the entire chip fits together in this block diagram that also roughly corresponds to the physical layout on the chip. 34 ET minion shires contain 1,088 ET minion processors. On the left and right sides, 8 memory shires contain the LPDDR4X DRAM controllers. On the top right, 1 Maxion IO shire contains the 4 ET Maxions and most of the other small IO signals, and 1 PCIe shire contains a Gen 4 PCIe interface. Maximum chip power can be set with a software API, but for recommendation tasks, we expect a typical operating point will be under 20 watts. Here are the external chip interfaces, but you'll need to zoom into the slide later to see the details. Let's look at how the Esperanto chip might be used in a real system. Esperanto's low power technology allows 6 Esperanto chips and 24 64-bit wide DRAM chips to fit into the 120 watt power budget of the customer's PCIe card. One accelerator chip can hold up to 192 gigabytes of DRAM, providing up to 822 gigabytes per second of memory bandwidth. By using multiple chips, we can effectively have a 1,536-bit wide memory interface using low-cost and low-power LPDDR4X DRAM, which would have been way too many pins for a single chip solution. This one accelerator card has over 6,000 RISC-V cores and 12,000 threads of execution, helps provide a good way to handle memory latency for the memory-intensive portions of recommendation models. Here's a picture of how the 6 Esperanto chips could fit on an Open Compute Project Glacier Point version 2 card. Each Esperanto chip is mounted on an OCP-compliant dual M.2 module that also contains DRAM, flash memory, power supplies, and other circuitry. Peak performance for this one card would be over 800 teraops of int8 when all the ET minions are operating at 1 gigahertz. Here's an example of how Esperanto's chip could be deployed at scale in existing OCP data centers. 6 chips mounted on 6 dual M.2 cards can be plugged into the 1 Glacier Point V2 accelerator card. 2 Glacier Point V2 cards fit into a Yosemite V2 dual x86 server sled for a total of 12 chips. 4 Yosemite sleds fit in a cubby, 8 cubbies fit in an OCP rack. Therefore, each rack could hold 384 Esperanto chips. And with thousands of racks in a large data center could potentially deploy millions of Esperanto accelerator chips. Of course, software is the key to making all the hardware work, and Esperanto will support C++, PyTorch, and other common ML frameworks. Our first ML compiler is based upon GLOW, and we're also adding support for TVM. The compiler front ends do hardware-independent optimizations, including dividing the work to run across multiple chips. The compiler backends are modified by Esperanto to generate low-level machine instructions for the Esperanto chip. Now let's look at some performance comparisons for recommendation. We use the MLPerf Deep Learning Recommendation Model benchmark scores as reported on the mlcommons.org website by the respective vendors, except for Esperanto, where we give our projected performance. See the footnotes for all the details. The light green bars compare the relative performance of each accelerator card to the performance contributed by one server chip. The dark green bar charts compare the relative performance per watt of each accelerator card to the TDP power of one server chip. So for example, the MLPerf DLRM score for Intel was reported as 24,630 using 8 server chips. We divided that number by 8 to get the 3,079 samples per second for one chip. The performance and power numbers used for comparison of the bar charts here are shown in bold. One 120-watt accelerator card with 6 Esperanto chips has 59 times more performance than one 250-watt Intel server chip. Our position is that performance per watt is actually a better metric of performance, since everyone ought to be measured at similar power usage. Esperanto expects our performance per watt to be over 123 times better than the server chip. So now I'm sure you're thinking, okay, that's a great recommendation score, but what's your drystone score? Okay, I'm just joking. I didn't really mean drystone. I meant ResNet 50, which is the drystone of our day. It's not a great benchmark either, but one that still everyone wants to see. So for comparisons, we've taken the best ResNet 50 scores reported by each of these vendors from the respective company websites and power from the data sheets. The formatted approach is like the prior slide, and again, see the footnotes for all the details. The numbers being compared here are shown in bold. Even on this compute-dense benchmark, Esperanto expects to have over 25 times better performance per watt than the Intel server chip. For standalone operation running Linux, or for portions of workloads that are not parallelizable, the Esperanto chip also includes 4 high-performance ET Maxion processors. The Maxions were not used in the ML recommendation benchmark shown today, and since we've described the Maxion in detail elsewhere, please see those references for more information. The Esperanto supercomputer on a chip has been fabricated in TSMC 7-nanometer technology and contains over 24 billion transistors. You can see the various chip stats here. All the performance numbers for Esperanto shown so far are projections based upon gate-level simulations of the entire chip on a large Synopsys ZeBu hardware emulation system. The time of this recording, we recently received silicon in our labs, and we're in the process of bringing up chip testing. Here's the first 7-nanometer chip mounted in the package. Results on silicon in systems will be reported after we've completed bring up and software tuning. The Esperanto supercomputer on a chip is the highest performance commercial RISC-V chip announced so far. It has the most RISC-V cores on a single chip. It has the most RISC-V aggregate instructions per second on a single chip. And it has the highest number of teraops on a chip driven by RISC-V cores. Esperanto's low voltage technology provides differentiated RISC-V processors with the best performance per watt. We hope we've convinced you that energy efficiency matters and that the best way to compare performance is to compare performance per watt. Making an energy efficient parallel processing system required many innovations and trade-offs between the processor and memory system architecture and the circuits and low voltage techniques that improve energy efficiency. Now we have that hardware part done, and we can take this modular architecture and easily scale it either up or down and port it to other semiconductor processes. If you're interested in becoming a customer of our chip, boards, or a full evaluation system, just send an email to chips@esperanto.ai. Thanks for attending our talk, and we hope to hear from you.
We have quite a few questions from the audience, so let's get started. David from ML Comments asks, one of the challenges with operating in such a low supply voltage is the increased sensitivity to variation and operating conditions. Do you have any data to share on that?
Well, collecting data on variation is a lengthy process. It's probably going to take actually several months and processing a lot of labor to get really good data. But having experience with VP variation in many projects in the past, we put in a number of VP variation mitigating approaches on our chip. One of the ones I mentioned in the talk is each named Shire is able to have its own separate voltage supply that's independently tunable. I think as we bring up the chip, we'll see really what happens on the silicon, but we don't think the variation problem is going to be a terrible problem, particularly at the voltages we're operating at.
All right.
It's very clearly not sub-threshold, it's not even near threshold logic.
Thanks. And John from Red Hat is asking, energy cost is heavily impacted by external memories and IOs. How much does that add above the 20 watts that were quoted?
Well, the IOs are for our chip are already included here. In fact, for simplicity of the hot chips presentation, we really would have all of that together. So when I'm talking about 20 watts, I'm actually including the DRAM and the miscellaneous components that are on the board. DRAM itself, because we're using LPDDR DRAM, is only a little over a watt for the 4 DRAMs that we utilize. And again, because we have so much memory on board, we're able to keep a lot of the memory traffic on chip. So we're roughly in that scope. And the way it works is there will be a software API, and we'll simply say, for example, the entire N.2 module in that one example, that module should not take more than 20 watts. And the system will automatically adjust the voltage and frequency to keep this total system power less than that. And that way, when you're doing something which is very memory bound, for example, maybe the external memory takes a little bit more power, but the internal core is not computing as much, and it takes less power. So we can adjust it so that the sum total of all the different components on the board is below any particular power threshold.
Got it. Nathan from Insight64 asks, why did you decide not to support bfloat 16?
Okay. It's a slightly tricky answer in that the hardware in some sense does support native bfloat 16. bfloat 16, for those who aren't familiar, is simply an FP32 number minus the lower 2 bytes of Tensor. So if you wanted to, and quite often bfloat 16 is used as a storage format. So what we would do is expand it to a 32-bit float for the computation and then store it back out as a 16-bit bfloat 16 number. However, why don't support it natively? Because the throughput will only be half as much as a 16-bit float than doing it this way. And the answer is that because we're doing inference, we went to talk to one of our primary customers and said, hey, if we had pure support for bfloat 16, It only delayed our project by a couple of weeks. I said, look, we do not use B+16 for inference. B+16 is primarily for training. Really, we would advise you not to implement native support the way you have it supported right now. Using it as a subset of HC32 is more than sufficient. So that's the reason we didn't expand the instruction set, which would have consumed a lot more opcode space for a set of B+16 for inference. As we go forward, though, in future generations for training, that's something that's fairly trivial to add.
All right. Manoj from Synopsys asks, since your goal was to make a relatively general purpose accelerator, how did you think about sizing the data cache?
So remember, when you have 1,000 cores on a chip, area is really primary. So there were a couple of considerations, area being one of them. And so by shifting an area to make the L1 data cache smaller, you depend more on the level 2 cache. So having a multi-level cache system is actually important here. A lot of accelerators don't want to do that because it does add some complexity. The other issue is one of the special circuits we had to use. So in order to keep very robust operation at low voltage, we had to use an SRM cell, which was substantially larger in area in order to get that robustness. So again, that made me wanted a fairly small level 1 cache. So we gone with a 4 kilobyte level 1 data cache. That gave us a high enough hit rate for what we wanted to do for Tensor operations, and it scheduled very well with the tightly integrated level 2 cache. That those were appropriate ratios. And from then on, it's pretty much using standard formulas for thinking about how you size caches from level 1, level 2, out to your main memory for picking sizes. But that size actually worked fairly well for us. We kept the area per million small, so that we multiply by 1,000, we still can fit 1,000 full general purpose 64-bit processors on a single chip.
All right, that was the last question. Dave, thank you very much again. Exciting architecture. Waiting to hear from more from you guys.
Okay, thanks very much.
All right, our next talk is by Ryan Liu and Feng from Enflame, who will introduce us to the DTU-1. That's Enflame's first generation AI accelerator. Ryan is the chief architect of Enflame, leading the AI acceleration chip architecture group, and Chuang is the design director for the deep learning engineering group. Ryan, Chuang.
Hello, everybody. I'm Ryan Liu from Enflame. I and my colleague Feng today will introduce you the first generation AI chip from Enflame. This chip was designed 2018 and launched at the end of 2019. We call this chip DTU 1.0, the Deep Thinking Unit 1.0. It is a high-performance computing accelerator chip for cloud AI training scenarios. It supports multiple types of the network models, such as CNN, RN, LSTM, and BERT, and which variety of data types, IP62, IP16, BF16, int8, int16, int32. It is optimized for data centers, large-scale training workload, and provide excellent energy efficiency. DTU was made by 12-nanometer FinFET process. It contains 14.1 billion transistors and can provide maximum 20 teraflops computing power at P632 precision and 80 teraflops computing power at P16 and BF16. It also supports 16 lanes PCIe Gen 4 provide 64 gigabytes per second bidirectional host bandwidth. It also supports up to 200 gigabytes per second bidirectional chip-to-chip interconnection bandwidth, which is very important to high-performance computing and AI training workload. DTU is made by 2.5D package. It integrates 3 chips, as you can see in the diagram, one computing die and 2 HBM chips. This chip supports up to 300 watt computing power. This is the top diagram of Ditzel SoC architecture. Ditzel is designed to be a fully programmable chip. Its computing die has 32 AI computing cores. Each core has a general computing engine which can be programmed for scalar, vector, and tensor operators with multiple data types. Ditzel groups its 32 cores into 4 clusters. Each cluster has 8 cores with shared on-chip L2 buffer. Cluster and 2 high bandwidth memory HBM, which provide 512 gigabytes per second bandwidth, are connected through on-chip network. With software scheduling algorithm, they are easily being programmed for data parallel and module parallel computing. There were 40 data transfer engines, which support shaping tensor data during data movement between memory hierarchies to provide maximum computing efficiency. At the right bottom, there were 4 high-speed, low-latency inter-chip connectors, which can easily extend from single chip to large-scale computing metrics. Now, I will introduce my colleague Chuang to bring more details for the computing cores.
Thank you, Ryan. We call those AI cores as GCU Care 1.0. It is a VLW processor. As shown in the diagram, the core has an L1 instruction memory with a size of 64 kilobytes and L1 data memory with a size of 256 kilobytes, and a DMA engine with a 1 kbit bus interface. It has a scalar ALU for control and a group of tensor ALU kernels for both vector and matrix operations. Correspondingly, the core has scalar, vector, and matrix register files. The supported data formats, as mentioned by Ryan, and the tensor kernels are 8-bit, 16-bit, 32-bit integers, and FP16, bfloat16, FP32. There are totally 256 tensor kernels shown in the red blocks. Each kernel supports 1 32-bit MAC, 4 16-bit MAC, and 4 8-bit MAC. Each kernel supports all the data formats and supports mixed precision operation as well. Data broadcasting happens among those kernels to maximize the data reuse and reduce wiring requirements. Counting all those kernels, each single core supports 256 MAC per cycle for 32-bit operations and 1K MAC per cycle for 8-bit and 16-bit operations. With 32 cores in DTU 1.0 SoC running at 1.25 GHz, we will have 20 teraflops for 32-bit operations and 80 teraflops or TOPS for 8-bit and 16-bit tensor operations. To fully utilize the data sparsity, those kernels will get ALU logic or fully skip the instruction if there is a zero power operation detected. Thus, the compute core as well as the compute ALU unit's power will both shrink with the data sparsity increasing. In addition to tensor operations, 32 kernels among those, the green part showing diagram supports general vector operations, including instruction acceleration for transcendental functions. Its vector length is of 1 kbit, while L1 supports 2 kbit per cycle for load and 1 kbit per cycle for store. Based on data element format, the core will use 32, 64, and 128 kernels for VMAC operations, including both the green ones and the pink ones. One upper element uses 1 kernel, same as tensor operations. 2 specific operations, sum and pooling, are supported as well for those green and pink kernels. Diagram left is showing the sum operation. Every time 4 elements are summed together, and the result is written into matrix registers. Depending on the data format, every time there will be 8 or 16 or 32 elements being generated. Diagram right is showing the element pooling operation. Still, every time 4 elements are selected from the vector register and choose the maximum one out of them. The difference is that the 4 element groups can overlap with each other based on different stride, as shown in the picture. And at the beginning or the end of the vector register, there may be padding elements added by hardware. Also, the pooling instruction can select which elements are targeted elements in the pooling operation by using a mask indicator. In this way, the core can directly do pooling operation and reuse data on HW element plane. All those 256 kernels work together to support the convolution operation. In each operation, 256 elements are generated and written in matrix registers. It can support register file write cancelling. So, if there are accumulation to the same feature points detected, the redundant write to register files will be cancelled to save power. Input feature and weight come from the vector registers. In case of 16-bit operations, dot product 4 is used and the different groups of weights are not overlapping with each other. In the feature side, it is similar to pooling operation. The hardware will support padding, stride between sample features, and reuse features from HW plane if possible. Different kernels may share features or share weight based on the tensor shape, which will be shown later. Gem is similar to convolution, with the difference that there's no overlapping between input. To maximize the data reuse, processor core supports various tensor shape. We define the output shape as the tensor shape. In 32-bit operation, it supports 8 by 32, 32 by 8, and 16 by 16. In 16-bit operation, it supports 64 by 4, 32 by 8, and 16 by 16. In 8-bit operation, it supports the most. Even 128 by 2 is supported. Physically, the 256 tensor kernels are distributed into 4 physical partitions, and we call them 4 kgs. Each kg is fed with 1 kbit input data and has 5 12-bit output data. Kernels are selectively enabled in each instruction based on the output point number. Now let's talk about the memory hierarchy and the data transfer engine GCU there. We have 2 HBM providing file 12 GB per second, and L2 buffers in 4 clusters provide 5 TB per second, and all L1 buffers together providing 10 TB per second, feeding the register file and the LU. Asynchronous data flow are provided by the data transfer engine GCU there, and the sync operation as well as dependency management are defined in software programming model to ensure full pipeline between data flow and compute. Their operation is based on 4-dimension tensors, and various in-data flow tensor operations are supported to enhance the efficiency. Diagram here shows a slicing and a deslicing operation between the source and destination, which is quite frequently used in the data flow. It also supports the reshape between dimensions to make the data layout being friendly for compute engine. In addition, padding, concatenating, broadcasting, downsampling, etc. can also be used. Okay, let's back to Ryan.
Thanks, Chuang. Here, let me continue the part of inter-chip connections. We call this GCU lab port. It shares the combo analog file of PCI Gen 4, at a speed up to 25 gigabits per second lane, and with in-house designed protocol, it has much less point-to-point latency, which is within 1 microsecond. Each chip has 200 gigabytes per second bidirectional bandwidth per card, and 800 gigabytes per second interconnection speed inside single server. With commonly used hybrid cube mesh topology, we can easily form two bidirectional rings to connect 8 chips in the server with all bandwidth fully leveraged. And it also supports to split the usage of a server into 2 or 4 parts with good performance. As shown in picture, DTU can use layer cable to extend the connection to a rack without DMA. Cloud Blazer, the AI training accelerator standard card designed for cloud data centers, is based on DTU chip. There were 2 models. T10 is a standard 225-watt PCIe accelerator card, and T11 is an OM module which supports up to 300-watt TDP power with better performance. Enflame distributed training solution provides 3 connectivity specifications for small, medium, and large data centers to meet deep learning training needs of different customers based on scale, performance, and cost. The first, single node model, standard PCIe card in single server node with 8 or 16 Cloud Blazer T10 cards to meet small scale deep learning training needs. Single node model can be smoothly expanded to single rack or large scale cluster model. The second, single rack model. This involves a single rack to provide AI computing power. It is applicable to large to medium companies and scientific research institutions for deep learning training. The single rack model can be expanded to cluster model as well. The last but the most important, cluster model. Through GCU layer and RDMA, it forms large-scale cluster. It can be used in super-scale scenarios. 2D torus topology is used to meet the needs of E-class data center in terms of scale and cost. This diagram are some of the results measured in real system. Left diagram is the performance of an 160 cards cluster. It achieved more than 90% linearity in a single server with 8 cards. And it also achieved more than 8% linearity in the full 160 card cluster. The right diagram are some of the results of the training, which are very the same as GPU AP32 precision training result. Above all about the DTU 1.0. Then comes to my favorite slide. What's the next? This July, Enflame launched our 2nd generation AI training chip, DTU 2.0. Compared with the 1st generation, which launched 2 years ago, it's improved dramatically on computing power, memory capacity, and bandwidth, interconnection capability. With the same process as DTU 1.0, the new chip boosts its computing power of floating point 32 almost 2 times. It also introduced the Tensor float 32 precision into the chip and provides almost 8 times 32-bit floating point computing power compared with the 1st generation. In the meantime, with the new generation of HBM memory, DTU 2.0, gets almost 3 times of memory bandwidth and up to 4 times memory capacity, which is very useful for AI training workload, especially for huge size model supporting. This new product will be ready for shipping soon. Okay, that's all of my part. Thank you very much for listening.
Thanks, Ryan, Chuang. Great work. You definitely left us curious with what's coming up next with DTU 2. Let's go to the Q&A part. David is asking, is there a particular training workload that you guys are targeting? For example, recommendation workloads, vision, natural language processing?
Okay. For this training workload, typically we supporting the vision, the workload we supporting the vision and NLP, such as NLP, and our first landing customer was using that in the reinforced learning.
All right. Christoph asks, why did you decide to design your own chip-to-chip interconnect protocol, and is it cache coherent?
Oh, this lab protocol that is okay. It's not cache coherent. We provide that memory copy plus the data sync mailbox symbol to make that connector. And the reason why that we developed that in-house design protocol is because we want to have a much light protocol and which can get better latency performance.
All right, and last one, Ian from Anantech is asking, do you have intention to sell this part to the West? And what are the plans there? Is it a direct contact with Enflame or sell a system through an OEM?
Well, currently our customer is mainly in the Asia, but yeah, if you have interest to our product, please come to Enflame directly.
All right. Guys, thank you very much. It was a great talk. You left us curious with what's coming up next, and I appreciate your time. All right, our last talk for this session is by Karam Chatha from Qualcomm. Karam is a senior director at Qualcomm, where he leads the engineering team for the Cloud AI 100 project. Cloud AI 100 is a scalable inference accelerator targeting both data center and edge inference workloads with a single chip. So Karam, take it away.
I'm Karam Chatha, and I lead the engineering team that designed and implemented Cloud AI 100. The Cloud AI 100 is a purpose-built solution for accelerating inference workloads in cloud and edge infrastructure. It's an extremely high performance and power efficient accelerator. And for typical AI operations, it can deliver over 12 TOPS per watt of performance. So let us begin with the motivation. AI has become ubiquitous in data centers, from social media to e-commerce and industrial applications. All of them are leveraging this exciting and new technology. However, at the same time, the cloud infrastructure has been under extreme pressure. Data center power consumption has been doubling every year. AI workloads tend to be compute intensive, and therefore they are only adding to this exponential trend. So there is an urgent need for high performance and power efficient inference acceleration in data centers. What we are advocating is an heterogeneous approach of pairing up a general purpose server with several of these purpose-built energy efficient AI accelerators to relieve the pressure on the cloud infrastructure. Qualcomm has been at the forefront of AI research, and particularly AI inference research, for over 13 years. We are now on our 6th generation of our inference engine. We deployed our first purpose-built inference engine on a mobile platform back in 2016. what we are doing with Cloud AI 100 is essentially leveraging the same expertise that we have in high performance and low power inference and scaling it up to address the workloads for cloud and edge. So Cloud AI 100 comes in two form factors: a high performance form factor of PCIe half height, half length, consuming up to 75 watts. This is typically aimed at cloud infrastructure, and a more power efficient dual M.2 form factor with a scalable TDP of 15, 20, or 25 watts. And this is aimed more at edge applications. The focus is on ML inference. And we are actively collaborating with several industry leaders for deploying this solution. So with that background, let us look under the hood of the Cloud AI 100. So what I'm showing you in this figure is the top level SoC view of the AI 100. It's a bespoke high performance architecture for deep learning inference. As you can see, it's a homogeneous multi-core architecture consisting of 16 AI cores, what we call AI cores. At its peak, the SoC is able to deliver over 400 TOPS of int8 and 200 FLOPS of FP16 performance. It has a large on-chip memory, over 144 MB of on-chip memory. And what this allows us to do is, for many of the networks, store all the weights on the SoC itself, thereby improving performance and at the same time reducing the power consumption. It is a high-speed NOC that can support over 186 gigabytes per second for intercore communication. The high-speed NOC has support for multicast and intercore synchronization. In terms of the interface to the host, it's via an 8-lane PCIe Gen 4. We provide over 136 gigabytes per second of LPDDR4X. It has capabilities for secure boot and RAS. And it comes with a fairly sophisticated power management solution that is able to limit the power consumption at multiple levels of hierarchy, from the AI core itself to the SoC to the board level. So on this slide, I'm showing you the top-level view of the Qualcomm AI core. So on the AI 100 SoC, we have 16 of these cores. As I mentioned earlier, this core is derived from our mobile solutions. However, we have upped the performance capabilities to address the cloud and edge workloads. So it has a scalar core, which is a 4-way VLIW core. It has a very rich instruction set of over 1,800 instructions. It's a multi-threaded scalar core. It has 1 MB of L2 cache, and it supports int8, int16, FP16, and FP32 precisions. We have a tightly coupled memory, which we call the VTCM. And it has 8 MB of memory. And what it allows us to do is store the weights on the SoC itself. It's accessible by the scalar unit, the vector unit, and the tensor unit. In terms of acceleration, we have the vector unit, which comes with a very rich instruction set for AI, CV, and image processing. It supports over 700 instructions. In terms of precision, it supports int8, int16, FP16, and FP32. At its peak, it can deliver 512 of int8 and 256 of FP16 max per clock cycle. Then we have the tensor unit, which is a high-performance and low-power accelerator for linear algebra. It supports int8 and FP16 precision formats. It can deliver over 8K int8 max per clock cycle and over 4K FP16 max per clock cycle. Now that you have a sense of the SoC, let's delve into a little bit about the power efficiency of this architecture. So what I'm showing you on the left-hand side is 3 SoC operating 12-watt mode, which is suitable for edge applications, about 20 watts, 20-watt mode, which can be utilized for edge and ADAS applications, and finally a high-performance mode of about 70 watts. The workload that we are executing on the SoC is a 3x3 convolution operation. This is common in many deep learning models. In terms of the input to the 3x3 convolution, we assume 50% zeros on the activation data. This is again quite common, where if the CNN has a ReLU operations, you do end up with about 50% zero on the activation data. The weights for the computation are uniformly distributed. So if you look at the most power efficient operating mode, we are able to deliver about 150 TOPS of performance at about 12 watts with an SoC TOPS per watt of 12.37. Similarly, we can deliver close to 200 TOPS of performance at about 20 watts of power consumption, and the TOPS per watt are very close to 10. And finally, in the high performance mode, we can deliver over 360 TOPS of performance at about 70 watts of power for an SoC TOPS per watt of 5. There are really 4 primary reasons that allow us to achieve this high TOPS per watt. The SoC architecture itself is, as I mentioned earlier, is specialized for AI inference. We are utilizing an industry-leading low-power IP from mobile. It's an extremely mature IP which has been specialized for inference, and we are now on the 6th generation of the IP. The SoC is fabricated in an advanced technology node of 7 nanometer. And finally, the solution comes with a sophisticated compiler that is able to effectively exploit the multi-core architecture to deliver high performance at extremely power-efficient operating points. The Cloud AI 100 comes with a complete software stack for AI inference. It can support applications from computer vision to speech to ADAS, NLP, and recommendation systems. In terms of models, I'm showing you a handful of models on the slide, but the solution itself can support over 100 models across the application domains that I just mentioned. In terms of ML frameworks, it can support all the prevalent ML frameworks, including TensorFlow, PyTorch, Caffe, and Caffe2. It supports the ONNX exchange format. It supports ONNX runtime. The software itself comes as 2 SDKs, the apps SDK that includes the compiler, the simulator, and some sample codes, and the AIC platform SDK that you need to launch an inference onto the hardware. So it includes the runtime and the drivers. The compiler, as I mentioned, is a key component of the solution. And in the next few slides, I'm going to give you a little bit more details about the compiler and discuss some of the key optimizations. The Cloud AI 100 parallelizing compiler translates the high-level description of a neural network into machine code. It parallelizes inference computation across the multi-core SoC. It splits the data across the AI cores and synchronizes computation. It parallelizes across tensor, vector, and scalar operations. And it supports int8, FP16, and mixed precision operations. It performs its optimizations in 3 phases: high-level optimizations that operate at the graph level, instruction level optimizations that operate on a deep learning operator, and they are focused on buffer and memory reuse. And finally, LLVM higher level optimization. So a parallelizing compiler needs to be able to effectively search the design space to come up with the best parallelization scheme for a particular network. In the following 2 slides, I'm going to walk you through some of the key optimizations that are deployed by the compiler. On this slide, I'm going to discuss some of the parallelization trade-offs that are performed by the compiler in the context of 3D convolution. So the input to the convolution operation is a 3D data of input activations and several kernels. And the objective is to produce an output activation data, which is also 3D in nature. Now, in terms of parallelization, one could do parallelization by having each AI core compute a subset of the output activation. So each AI core will compute some of the channels associated with the output activation. So there's less duplication of weights. However, there's increased multicast to share the results. This optimization tends to be the best for VTCM usage, but incurs the penalty of multicasting of activations. One could also parallelize by batch elements. So each AI core will compute the output activation associated with a single batch element of the input. So this scheme will reduces the multicast traffic, but it has very high VTCM utilization. The entire weights need to be stored on the TCM of each AI core, and therefore there is high VTCM utilization. So this tends to be the worst optimization from VTCM memory utilization perspective, but indeed gives the best performance if the network fits completely on the SoC. Finally, one can also do the parallelization across spatial dimensions. So the input is split spatially in X and Y dimension. This reduces the size of intermediate activations, so there is less multicasting. But then the penalty that we pay here is that there is duplication of weights. So as you can see, for just parallelizing a convolution operation, the compiler needs to explore a fairly large design space, and it's able to effectively do that and pick the best parallelization scheme based on the dimensions of the convolution operation. On this slide, I'm going to talk about a few other key optimizations that the compiler performs. I'll begin with what we call depth-first processing. So in typical data parallel computation, one would compute the data associated with a particular layer, the complete data set associated with a particular layer, and then use that to generate the data associated with the next layer. So you would compute the entire data associated with the first layer, and then use that data to produce the data for the red layer, and then use the entire data of the red layer to produce the data for the blue layer, and so on. And so this is classical data parallel computation, but this puts an extreme pressure on the VTCM memory. Typically, these activations tend to be very large, and therefore there is spillage from the VTCM memory, which adversely impacts the performance. Now, if you're going to be performing this computation, it's not necessary to compute the entire data associated with a particular layer. So, for example, one could take a subset of the input from the dark green layer to produce a subset of the output for the red layer, and then use that to produce a subset of the output for the blue layer, and finally to produce a sliver of the output for the light green layer. So in this way, we are not writing the intermediate layers to DDR. The depth-first processing effectively minimizes the spillage to DDR, and it is extremely effective for large resolution images. In particular, for ResNet 34 SSD that has over 1.4 MB of input resolution, depth-first scheduling gives over 5x lower DDR bandwidth, 3x higher inferences per second, and 2x higher inferences per second per watt. The compiler is also able to perform scheduling to minimize peak power excursions. So if you were to perform 3D convolution in a data parallel manner, then it is quite possible that all the tensor units across the 16 cores light up at the same time. This causes peak current surges, or also otherwise known as DIDT events. So what the compiler is able to do is it's able to schedule the computation such that it can minimize the possibility of these DIDT events. Finally, the compiler also generates metadata that can be utilized by the controls loop, the limits control loop that are on the SoC, to quickly settle upon the most efficient voltage frequency operating point for a particular workload. The Cloud AI 100 is also able to split a single network across multiple cards. This capability is particularly useful for large NLP models that do not fit within the DDR of a single card. For certain other networks, this partitioning across multiple cards allows the network to reside in the TCMs of all the cards. So the entire network is only resident in the TCM of in each of the cards, and this also helps in improving performance. The software supports peer-to-peer communication between the cards through the PCI switch. So we do not pay the penalty of going through the host. It's an extremely low latency. It supports low latency transfer between two peer cards. Cloud AI 100 also comes with a AI model efficiency toolkit, otherwise known as Aimet. Aimet supports quantization for int 8, int 4, and int 16. It supports quantization-aware training. It supports model compression by SVD and other techniques. And then it also is able to generate mixed precision models that include both FP16 and int 8 operations for satisfying the accuracy associated with that particular model. Aimet is open source, so you can download it from the Qualcomm web pages. In the next few slides, I'm going to be discussing performance results for some of the typical deep learning benchmarks. On this table, I'm showing you 3 CV benchmarks: ResNet 50, ResNet 34 SST, and MobileNet V1 SST, and 2 NLP benchmarks, BERT-based and BERT-large. I'm showing you the performance for both 25-watt TDP configuration as well as the 75-watt TDP. As you can see, for ResNet 50, within 25 watts of TDP, we are able to deliver over 11,000 inferences per second. And at 75 watts, our performance is over 22,000 inferences per second. For ResNet 34, we are at 234 inferences per second. And again, at 75 watts, we are at 45. At 75 watts, we are at 424 inferences per second. On MobileNet V1, we are at about 12,500 inferences per second at 25 watts and north of 23,000 inferences per second at 75 watts. On BERT-based, we are 1,900 inferences per second on 25 watts and about 3,700 inferences per second on 75 watt TDP. And finally, for BERT-large, we are at 620 inferences per second for 25 watts and about 1,084 inferences per second for 75 watts. If you are conversant with the typically reported numbers for these benchmarks, you can see these are indeed industry-leading performance numbers for the given TDP. So the software, in particular the compiler, is able to give extremely high performance at very low batch sizes. Typically, low batch sizes imply low latency. So on the x-axis, I'm showing you the batch size. On the y-axis is the delivered inferences per second. For MobileNet V1, we are able to achieve the best performance with batch size of 4. So the performance is 23,000 inferences per second. And that's delivered by just a batch size of 4, and our latency is 12.3 milliseconds. On ResNet 50, we are able to deliver close to our best performance with a batch size of 4. Here, the latency is 3.4 milliseconds. Now, if you were to up the batch size, you do get a slight increase in performance of 22,000 inferences per second, and the latency is still quite low at 5.9 milliseconds. So what the Cloud AI 100 hardware and software together are able to do is not only deliver you high performance, but we are able, or high inferences per second, but we are able to deliver that high inferences per second at very low latency. On this slide, I'm showing you the capabilities of the Aimet infrastructure. So on the x-axis, as I mentioned earlier, Aimet is able to perform compression. It is able to perform compression via SVD and other techniques. So on the x-axis, I'm showing you the percentage reduction in operations for our ResNet 50 workload. On the left-hand side y-axis, I'm plotting the percentage increase in performance due to the reduction in those operations. So for about 25% reduction in operations, we are able to deliver over about 15% increased inferences per second on ResNet 50. Obviously, when you perform compression, there is a certain loss of accuracy. So the percentage reduction in accuracy is plotted on the right-hand side y-axis. And as you can see that for 25% reduction in operation, our loss in accuracy is only 1.1%. So our map score remains quite high, while we are able to improve the performance by 15%. This slide demonstrates the scalability of the solution. So on the left-hand side, I'm showing you the edge development toolkit. It consists of a Snapdragon 865, a Qualcomm AI 100 in the dual M.2 edge configuration, and a Snapdragon X55 5G modem. It can provide over 50 TOPS of AI processing in about 15 watts of TDP. And then on the right-hand side, I'm showing you a Gigabyte G292 Z43 cloud inference server. It supports over 16 PCI half-height, half-length cards. It can deliver 6 petaops of AI processing at about 2200 watts of TDP. In conclusion, the Cloud AI 100 is a scalable and power-efficient solution for inference acceleration across a gamut of product domains, including data centers, 5G edge boxes, ADAS, and 5G infrastructure. So I conclude my talk, and I'm open for questions. Thank you.
Thank you, Karam. These are quite impressive power performance numbers. We actually have a ton of questions from the Slack channel, so let's go to Q&A. Raj from Western Digital is asking, are the different performance to power points that you show, 12 watts, 20 watts, 70 watts, static configurations, or can the chip automatically adjust to these different points?
The chip has a very sophisticated dynamic voltage frequency switching scheme. So based on the power consumption, it's able to obviously change the voltage frequency for chip operation. Now, in terms of TDP settings, right? So based on your particular solution, you can specify 18 watts, 20 watts, 25 watts, or 75 watts. In that case, it becomes static. So the TDP settings are static. But in terms of the actual operating point, the chip has a sophisticated voltage frequency switching scheme to make sure that the power remains within the regulatory limits and of course the TDP limits within the settings.
All right. Ritika from NVIDIA asks, is the 12 stops per watt reference based on board level power measurements or chip level power measurements?
The 12 stops per watt is for the SoC. So it is the SoC power consumption.
All right. You're showing significant TOPS per watt improvement versus current solutions. So there's a question on what were the main drivers that enabled you to achieve this?
Good question. I think, fundamentally, that's a building on the building blocks, right? The IP that we have, the inference IP we have, and I cannot touch on that. I said that a couple of times within the talk. The IP is the sixth generation IP. We have been in this inference business for a very long time, right? We have been doing it high performance, low power inference, all the handsets, all your cell phones for a very, very long time. So we understand this domain, especially the inference domain, better than most folks do. And as a result of that, so the basic building block is extremely power efficient, right? It has the advanced on it for 7 years. So we start from there. Now, if you look at the basic building block, you sort of look at it, it's really a good architecture. So there's a lot of, the compiler is doing a fair bit of lifting, right? So when the compiler does a fair bit of lifting and is responsible for output at the start, you are relieving the burden of your hardware from having to work harder and then consume more power. Okay. Now, if you take that same thought process up to the SoC level, that's exactly what we have done. So what I have is we have blocks, high-speed blocks between the boards, sophisticated synchronous prediction mechanisms, but you don't have the assurance, right? So the multi-core architecture, again, it's a part like a compiler. It takes the same, what everybody knows about how do you schedule or how do you compile for data. It takes the same philosophy you make to the multi-core architecture. So the part like a compiler that we have is able to effectively distribute the architecture across the multi-core cores. It's able to, as I mentioned, it does several optimizations also to reduce the power, peak power consumption, network scaling, and so on. So that's the second element of it. The other thing is several nanometer technology. So that gives us an example. And finally, the system test architecture, right? We built this SOC bottom up. It's a bespoke architecture with the objective of doing extremely power efficient inference. So those are the sort of the four key elements that allow us to achieve this high inferences per second per one.
All right. There are actually a few questions that kind of follow quite naturally. So Salma from IBM asks, what are the trade-offs when you're picking between a VLIW architecture versus a RISC-based architecture for the different compute cores?
So I guess from our thought processes, right? What we have found is that the machine learning computation actually fits very, very well on a VLIW core, right? We have the technology with us, obviously, and so we have insights, we know how to build extremely efficient VLIW cores. But it is not just a matter of what we have. The workload itself actually is well suited for a VLIW core. And that's why we sort of have continued that, right? I mean, we obviously did evaluation of what we had to do something else, but we found that this was indeed the best way forward.
All right. There were quite a few questions on whether you can share details on the network on chip that you used. Is it a crossbar, a mesh, or anything else?
It is a hybrid topology. So it's not mesh, it's a hybrid topology. And you can sort of think about it as a sort of a more linear topology with the intermediate outputs if you make.
Okay. Moving to the software side, you mentioned a couple of compiler optimization, including splitting by batch, output channel, or a spatial dimension. And you also mentioned the depth-first scheduling optimization. So how does the compiler choose which optimizations to apply for which workload?
Good question. So right now, what we are able to do is basically you as a programmer can sort of choose, you can specify which one to apply via a compiler flag, which is similar to what you would do on a GCC compiler. We do have a model configurator that can basically explore through the various compiler flags that we have, and that way, if you don't want to be in the process of selecting a compiler flag, the model configurator is able to do that.
All right. Another question from Ritika from NVIDIA. Is the Tensor unit based on a systolic array or another technique?
It's not a systolic array. I think systolic array tends to be used rather broadly. So it is a 2D array of functional units, but if you sort of go by the book, then it does not necessarily conform to the systolic array diagnosis.
All right. And the question from Ameya, is the scalar core based on a RISC processor or something that you designed from scratch?
It's our own proprietary core. So it's a VLIW core, and it's our own proprietary core.
Got it. All right. This concludes our questions here. There are actually quite a few more on Slack, so I'm sure the audience will love to interact with you, Karam, offline.
Sure. Thanks for the opportunity. And then, if there are more questions, do catch me on Slack. I'll be happy to answer.
All right. Karam, thank you. And folks, this concludes our machine learning inference session.